Hey folks, Jim here with Science Talk. Um, Kind of an interesting little video I'm going to do for you. And basically, want to revisit the genius that was Wally Broker. Um, Gonna discuss a couple of papers that he was involved with. One from 1965 and another one from 1975. Now, this first one, Wally Broker was a contributor to this 1965 paper to the White House on restoring the quality of our environment, atmospheric carbon dioxide. Other researchers and authors involved: Roger Revelle, Charles Keeling, Harmon Craig, and Joseph Smagorinsky. Okay, so over here, kind of blew this up a little bit. Appendix Y4, atmospheric carbon dioxide. We see Roger Revelle is the chairman, and then the other four gentlemen. So they have the table of contents: carbon dioxide from fossil fuels, the invisible pollutant. With an intro, increase in atmospheric CO2, the partition of CO2 along the atmosphere, ocean, and biosphere. Probable future content of CO2 in the atmosphere, possible effects of increased atmospheric CO2 on the climate. Then other possible effects of an increase in atmospheric CO2: melting of the Antarctic ice cap, rise of sea level, warming of seawater, increased acidity of fresh waters, and now we know oceanic waters, increase in photosynthesis, other possible sources of CO2, oceanic warming, burning of limestone, decrease in the carbon content of soils, changes in the amount of organic matter in the ocean, changes in the carbon dioxide content of deep ocean water, changes in the volume of seawater, carbon dioxide from volcanoes, changes due to solution precipitation of carbonates. Then they go on to conclusions and finding detailed computations. All the things we have been discussing, all the things we've been seeing happening right back here. We're talking, what's this? Something like 57 years ago? They knew about it then. They were discussing it then. And what has been done in the intervening years? Diddly squat. We've made it worse. Okay. Some of the, section one: carbon dioxide from fossil fuels, the invisible pollutant. Okay, so from the introduction, only about 1/2000 of the atmosphere and 1/10,000 of the ocean are carbon dioxide. Yet, to living creatures, these small fractions are of vital importance. Carbon is the basic building block of organic compounds, and land plants obtain all their carbon from atmospheric carbon dioxide. Marine plants obtain carbon from the dissolved carbon dioxide in seawater, which depends for its concentration on an equilibrium with the carbon dioxide of the atmosphere. Well, it's not going to let me highlight that, huh? Well, equilibrium with the carbon dioxide of the atmosphere. Marine and terrestrial animals, including man, procure either directly or indirectly the substance of their bodies and the energy for living from the carbon compounds made by plants. All fuels used by man consist of carbon compounds produced by ancient or modern plants. The energy they contain was originally solar energy, transmuted through the biochemical process called photosynthesis. The carbon in every barrel of oil and every lump of coal, as well as in every block of limestone, was once present in the atmosphere as carbon dioxide. Over the past several billion years, very large quantities of carbon dioxide have entered the atmosphere from volcanoes. The total amount was at least 40,000 times the quantity of carbon dioxide now present in the air. 40,000 times. Now, keep in mind, this report was prepared and published in 1965, some 57 years ago. Most of it became combined with calcium or magnesium freed by the weathering of silicate rocks. It was precipitated on the seafloor as limestone or dolomite. I think of the Dolomite Mountains in Italy. About one-fourth of the total quantity, at least 10,000 times the present atmospheric carbon dioxide, was reduced by plants to organic carbon compounds and became buried as organic matter in the sediments. A small fraction of this organic matter was transformed into the concentrated deposit we call coal, petroleum, oil shales, tar sands, or natural gas. These are the fossil fuels that power the worldwide industrial civilization of our time. Throughout most of the 500,000 years of man's existence on Earth, right, obviously going back to like prior species, shall we say, his fuels consisted of wood and other remains of plants which had grown only a few years before they were burned. The effect of this burning on the content of atmospheric carbon dioxide was negligible because it only slightly speeded up the natural decay processes that continually recycle carbon from the biosphere to the atmosphere. During the last few centuries, however, man has begun to burn the carbon fuels that were locked in the sedimentary rocks over the 500 million years. And this combustion is measurably increasing the atmospheric CO2. Okay, let's pause and reflect on this. And basically saying that, when we're burning fossil fuels, it's like ancient sunlight being utilized. Makes all the sense that we now go to direct sunlight, use the solar energy directly. But it's also saying that when early on, we were just burning wood and plants. So it did not affect the atmospheric CO2 because that's basically a fresh, relatively recent source versus a source that's being sequestered away for many millennia, many millions of years. And notice he stated in the last several centuries. So obviously he's referring to the 1750 baseline that really is should be taken as the start of all of this, not as the IPCC continually keeps moving the damn goalposts. In the geologic past, the quantity of CO2 in the atmosphere was determined by the equilibrium between rates of weathering and photosynthesis and the rate of injection of volcanic carbon dioxide. Basically, you got a volcano that goes puff, and you inject the material into the atmosphere. On an Earth-wide average, both weathering and photosynthesis must speed up when the CO2 content of the air is increased. In other words, CO2 levels increase, then photosynthesis must also increase to draw down the CO2, and the weathering also draws down the CO2 through chemical reactions, creating carbonates, etc. So in other words, he's talking about negative feedback loops, which are corrective in nature. And on the flip side, it slows down when it is diminished. So if the CO2 levels decline, then photosynthesis will decline, and the chemical reactions involving with weathering will decline. Consequently, over geologic time, the carbon dioxide in the air must have risen when volcanic activity was high, must have gone down when volcanoes were quiescent. On a human scale, the times involved are very long. The known amounts of limestone organic carbon in the sediments indicate that the atmospheric CO2 has been changed 40,000 times during the past 4 billion years. Another cycle through. Consequently, the residence time of carbon in the atmosphere relative to sedimentary rock must be of the order of 100,000 years. The present rate of production of CO2 from fossil fuel combustion is about 100 times the average rate of release of calcium and magnesium from the weathering of silicate rocks. As long as this ratio holds, precipitation of metallic carbonates will be unable to maintain an unchanging content of CO2 in the atmosphere. Within a few short centuries, we are returning to the air a significant part of the carbon that was slowly extracted by plants and buried in the sediments during 500 million years. How many times have you heard me stress it's the rate of change? That's what he's getting at. The rate of change of us returning the carbon back to the atmosphere is far faster than the rate at which it was removed. Not all of this added carbon dioxide will remain in the air. Part of it will become dissolved in the ocean. Part will be taken up by the biosphere, chiefly in trees, other terrestrial plants, and the dead plant litter called humus. The part that remains in the atmosphere may have a significant effect on climate. Carbon dioxide is nearly transparent to visible light, but it is a strong absorber and back radiator of infrared radiation, particularly in the wavelengths from 12 to 18 microns. Consequently, an increase in atmospheric CO2 could act much like the glass in a greenhouse, raise the temperature of the lower air. Water vapor also absorbs infrared radiation both in a range of the CO2 band centered at 15 microns and at wavelengths near 6.3 microns. Micron is 10 to the, it's a micrometer, so it's 10 to the minus 6. Okay? So if you want to convert this into nanometers, just multiply by 1,000, so that you basically going to get, like 1 point nanometers, 10 to the minus 9. Yeah, so it'll be a factor of 1,000. With the average concentration of water vapor in the lower air at mid-latitudes, the effect of carbon dioxide absorption is reduced to about half that which would exist in an absolutely dry atmosphere. And he makes a reference to Merler in 1963. Ozone, which is an important constituent of the upper air, also absorbs some infrared at wavelengths around 9.6 microns, but its principal effect on air temperature is due to the absorption of ultraviolet and visible sunlight. The possibility, and UV is at the opposite end of the IR spectrum, right? The possibility of climate change resulting from changes in the quantity of atmospheric carbon dioxide was proposed independently, right? They're talking about possibility of climate change proposed independently by the American geologist T.C. Chamberlain in 1899 and the Swedish chemist Arenius in 1903. Think about that. Since their time, many scientists have dealt with one or another aspect of this question. But until very recently, there was little quantitative information about what has actually happened. Even today, we cannot make a useful prediction concerning the magnitude and nature of the possible climatic effects. Well, this is 1965. In the intervening 57 years, we've gotten a lot better at figuring this out. But we are able to say a good deal more than formally about the change in the quantity of atmospheric CO2 and about the partition of CO2 from fossil fuel combustion among the atmosphere, ocean, and the biosphere. Now, again, this is coming from something that came across my Twitter feed that Leon Simons shared. So my thanks to Leon Simons for sharing this. But want to point out this little table here. Recent increase in atmospheric carbon dioxide. So this is a table, starts in 1950, goes to 1962. So that is 13 years inclusive. and they break it down to coal, lignite, liquid hydrocarbons, natural gas, and then they sum it across. And then they present it as a percent of the atmospheric CO2 compared to 1950. So they're taking 1950 as a baseline. Now, think for a moment. How many videos have I done where we're looking at 1950 to 1980, thereabouts, as a 30-year baseline? How many things have I shared with you that Zach Labe has done where he's using 1950 to 1980 as the baseline? And in atmospheric sciences, they tend to use 30-year averages. So they go 50 to 80, 60 to 90, that kind of stuff there. It seems to be their convention. Why is that? Because Wally Broker did it. It's also when we have pretty decent data. You can find the roots of that right here. So, in some ways, that's better because if you want to, say, compare the average global temperature today, but if you're going to compare that to 1990, well, it's not going to differ that much, but you compare it to 1950, yeah, it does. If you compare the average global temperature today to 2010 versus 1950. So I actually prefer sticking to that baseline of comparison to 1950 so that you get a sense of the overall magnitude of the change. Now, if you want to look for decadal trends, sure, then you compare it to 2010, 2000, etc., etc. You can do those comparisons. Nothing wrong with that. But if you want to get an idea of the extent of the change, yeah, go back to 1950. Just like, looking at ocean heat content since 1971, right? You've heard me stress that aspect when I made those videos examining ocean heat content. So now he cites here during the 5 years 58 through 62, 5.3 times 10 to the 16 grams of CO2 were produced by the combustion of these compounds there. Okay, so let's look at from 1958. That's this line here. Okay, so for coal, it was 0.46 times 10 to the 16 grams. Okay, and then you do the same thing for lignite, 0.14 times 10 to the 16. So all the numbers we see here, multiply this by 10 to the 16 to get total grams. So then what he does is they sum it up across so that the total is 0.97. Then the next year, again, sum it up across 1.03. So here's 2 times 10 to the 16 grams right there. And then 1.08, 1.09, 1.15. So in these 5 years, so when he total this column here from 1950 to 62, it's 11.6 times 10 to the 16 grams of CO2. And in these 5 years, 5.3, almost half of it, of this total, almost half of it was produced in those 5 years. And if you go 6 years, then over half of it was produced. And then you can see the increasing percentage comprising in the atmosphere. So we're already seeing a clear trend of how the atmosphere CO2 levels are increasing. One other thing I want to share with you from a paper published in 1975. Climatic change. Are we on the brink of a pronounced global warming? Who's the author? Oh yeah, that guy, Wally Broker. Okay, appeared in Science. Let's read through the abstract. If man-made dust is unimportant as a major source of climatic change, then a strong case can be made that the present cooling trend will, within a decade or so, give way to a pronounced warming induced by carbon dioxide. By analogy with similar events in the past, the natural climatic cooling, which since 1940 has more than compensated for the carbon dioxide effect, will soon bottom out. Once this happens, the exponential rise in the atmospheric carbon dioxide content will tend to become a significant factor, and by early in the next century, will have driven the mean planetary temperature beyond the limits experienced during the last 1,000 years. He called it. Now, he didn't quite get this correct because he was saying if man-made dust is unimportant. He's referring to the aerosol masking effect. We now know that the aerosol masking effect does impart a cooling aspect. Without the aerosol masking effect, as Guy McPherson has argued quite strongly and convincingly, without the AME, we would actually be even warmer than we are now. So, due to abilities to measure and of course model, Wally was not quite correct on that one. Be that as it may, but he said it's going to be exponentially increasing. That he got that spot on, and as we can see in the graph, whammo! Right here's 1975. Right here, whammo! That thing starts taking off. And we're on the track, the trajectory to incredible warming that is without parallel within human existence, and we're doing that. So you can see, I mean, if we look from say 1850 through 1925, a lot of ups and downs. If I was to run a regression through here, it'd be almost an insignificant slopes. In other words, slope of zero, no change. Then we start seeing an increase, and then it looks like it dipped down a bit. And that's this cooling that he's referring to, and then it takes off. Now, it could be other factors involved with this, but most likely the aerosol masking effect, for whatever reason, probably had a significant role in that. Atmospheric scientists will be able to address that better than I, but, keep in mind, he wrote this in 1975, so that's 47 years ago? And he called it exponential functions, exponential increase. So cannot overstate the genius that Wally Broker was and his enormous contributions to climate science. He basically developed the isotopic fractionation tool as a way to reconstruct past climates and to tell, certain things going on. For example, when the conveyor belt was running or not, etc., when there was ice sheets and other things. His traces in the sea, where he uses radionuclides to basically identify water masses in the ocean, deep water, intermediate water, that kind of stuff, and actually trace its motions throughout the ocean, and the mixing, etc. He did all that. He has, done so many things, introduced so many techniques, which we're still using. Of course, it's been modified over the years. We're still basically using the things that he did. He came up with the term the conveyor belt and showed how when that's running, the planet tends to be an interglacial. When it's not running, there tends to be an ice age. Glacial sheets develop and grow and expand. He did all of this. He's the grandfather of climate science. And here I am. I'm showing you something in 1975, something in 1965, and he called it. It's going to cause climatic change. We're going to see exponential increase in temperatures that's really going to change the climate. And the guy literally kept working until the day he died. Like he passed away in his office or something. So at age like 87. Yeah, never retired. So he was warning us, as were Chamberlain and Arenius were warning us, and we have chose to ignore their warnings, much to our peril. So on that note, thank you for your time.